Welcome to the third lecture in the Computing Systems class. This week's lecture is on binary representation and Boolean logic. We've already seen an introduction to binary representation and how single transistors can form simple electronic switches, a single bit that is either on or off, and how binary can be used to represent numbers and symbols. Now, in this lecture, we're going to build on this a little. We're going to start with logic. Logic circuits are the building blocks of computers. Have, to start with, Boolean values. These are simply true-false values, equivalent to on-off or the 1-0 values of binary. Boolean operations take some number of true-false inputs and give a true-false output. Here's a simple example, one we've already seen. This is a simple transistor inverter. The way this simple electronic circuit works is with a transistor whereby a signal at the base switches the transistor on or off. When the input signal is on, there's a connection between the Vout and the emitter. The emitter is at the low voltage value, so Vout will have the low value. When the input is off, on the other hand, there is no connection to the emitter, so the Vout value will be based on the VCC input, the high input voltage. Presence of a resistor there is what also makes this circuit work. The resistor is the wiggly line near the top of that diagram. This is also called a NOT gate. You can see the input-output diagram here. For an input of 0, the output is 1. For an input of 1, the output is 0. This simple type of table of inputs and outputs is commonly known as a truth table. By using different circuits of transistors and resistors, a range of basic logic gates can be built up. So our inverter, as we've already seen, is a NOT gate. 0 in becomes 1 out, and vice versa. Most other gates take 2 or more inputs. For example, AND will produce a 1 at the output if both inputs are a 1. So let's see some more of these logic gates just now. The top one is our NOT gate, our inverter. You can see here at the front of it we have a sort of triangle symbol and a small circle. The small circle is used in logic gate diagrams to indicate that the output is inverted. Without that circle, this would be essentially a delay. It would just output the same as the input, but might be a logic circuit that allows you to store the value for a brief moment in time before outputting it after a very, very small delay. So the input A is 0 or 1, and the output is not A. And what we have here at the truth table is we can see sort of shorthand, mathematical shorthand notation for writing not A. It would be to write A with the bar above it. We've already seen that. Our AND truth table is below. And again, for the output column, we have the mathematical shorthand A dot B for Boolean logic means A and B. And we can see here that the output is going to be 1 only when both A and B have an input value of 1. So there are 2 inputs to this small circuit. We just name them A and B, and 1 output. The truth table there again is fairly simple. And you can see we've got listed under the columns A and B every possible combination of inputs. So there are 4 possible combinations with 2 inputs. They can both be 0. A might be 0 and B might be 1. A might be 1 and B might be 0, or they can both be 1. So this part of the truth table, where we show the inputs, will be common to many of the basic truth tables for simple logic gates. Here are another 2. At the top, we've got the OR logic gate. And the OR logic gates output a 1 if A or B is 1. It still outputs a 1 if A and B is 1. Is A or B 1? Well, not only is A or B 1 in this case, both A and B are 1, but we still output a 1 here. And again, you can see the plus symbol here doesn't mean add A plus B, it means A or B. And so we can see the truth table, if both A and B are 0, the output of an OR operation is 0. If either one input is 1 or both inputs are 1, the output is 1. Fairly straightforward. The gate below is the NOR gate. As you can see, the symbol is quite similar, but there is a small circle in front of it. And again, that negates the output. So this is an OR gate negated. So it's not OR NOR for shorthand. And the truth table is the exact opposite output of the truth table above. So we've got the same truth table, but we've inverted the outputs. And this mathematical shorthand for this, we have A or B, and we have the bar above the whole thing to indicate that the whole thing has been negated. As well as doing the opposite of the OR gate, we can also do the opposite of the AND gate. So not AND or NAND. It's again indicated, the symbol is the AND gate symbol plus this small circle here. And we can see, looking at this truth table, again we've got the same range of inputs, and the output here is the opposite of the AND gate input. So for an AND gate, we only have a 1 output if both inputs are 1. Here, it's the other way around. We only have a 0 output if both inputs are 1. Otherwise, we have a 1 output for all the other possible combinations. And the other gate we're going to consider here is the XOR, sometimes called EOR. Basically means exclusive OR. So the symbol is similar to the OR symbol, but we have this extra line at the back. And so what's this truth table about? Well, this truth table is showing us that the output is going to be 1 when A or B is 1, but not when they are both 1. So it's exclusive OR. It's only when one or the other, but not both. So if A and B are both 0, the output is 0. If A and B are both 1, the output is 0. If A or B is 1, the output is 1. And you can see the symbol here for the mathematical shorthand is the same plus symbol used in the OR gate, but this time with a circle around it. So that's the exclusive OR shorthand notation. That's what individual logic gates do, and those are some of the most common ones. You can actually combine lots of different logic gates to try and build a larger circuit. For example, you can use NAND, and it should here say NOR gates. You can use NAND or NOR gates as building blocks to build other logic gates. For example, we can see here there's 2 NAND gates combined, where we've got 2 inputs. The output from one logic gate is fed into the next one, and then that is fed to the output. Remember, these are NAND gates. So very quickly, you can imagine, try and work out what's happening here. Well, this is a NAND gate, which will output a 0 if A and B are both 1. In all other cases, it's going to output a 1. Whatever the output is here is being fed to both inputs of this stage. Now, if you've got a NAND gate where both inputs have got the same value, so if both inputs are 0 into a NAND gate, the output is 1. If both inputs of a NAND gate are 1, the output is going to be 0. And if you can review back and you can look at the truth tables to verify that. So a NAND gate which takes one input and applies it to both inputs circuits, that acts as an inverter. So this section here is acting as a NOT gate. So we have NOT A and B, and then we have an additional NOT operation on the whole thing. To go back to the beginning, we have an AND gate. We've inverted the value, output, and we invert the output value again. So this whole circuit is showing us how to create an AND circuit from 2 NAND logic gates. In actually building integrated circuits, there is a tendency to focus on using either NAND or NOR logic gates as the building blocks for all other logic gates. The main reason for this is that it simplifies the construction of chips if there's a common base building block being used for all the circuitry. So overall, it may increase the number of transistors required to achieve a particular circuit in the end, but the construction is going to be simplified because there's only one basic logic gate circuit being used for everything. And so I've already answered that. The circuit shown there is an AND gate. And there's a wee challenge for you. Could you work out how to build an OR gate using only NAND gates? Or to build a NOR gate from only NAND gates? It is possible. And we had a wee quiz during the class to work out a circuit built from NAND gates. And you can again try this and see if you can work out the answer. The process for doing this, that I showed in class, was to try and use an intermediary truth table. So basically, to work out this answer, what we can do is try and work out what is going to be the value at this point. Well, this is going to be A NAND B. So we could call this, for example, C. So we can work out for all the possible values of A and B, all the possible combinations, and there's only 4 possible combinations. We could work out what the possible values of C are for each of those. And then this output here is going to be the output of A NAND C. And we could call this output D. And again, we could call this output E, and this is going to be the output of B NAND C. And then we can, again, one more step. We've got 2 values here. Can we find out what the output is going to be at the end here? Here's a first example of a useful circuit to be built using a couple of logic gates. This is actually quite a simple one, only using 2 logic gates. This is building something called a half adder. Our half adder has 2 inputs, A and B, and what it's going to try and do is add those up. And so what we have to imagine is, instead of thinking of them as Boolean true false values, we can think of them as numbers. Because they're binary values and there's only 1 bit, A and B are only the numbers 0 or 1. And our output S is going to be the result of the addition, and C is going to be a carry. Do we have to carry on a bit to the next column? If A and B are both 0, the sum is 0 and there is no carry. If A or B, but only A or B, is 1, then the sum is also 1 and there's no value to carry. But if A and B are both 1, the result is going to be a sum of 0, but we're going to have a 1 value to carry over to the next column. So one way of thinking of this, for example, is to consider if we added 0 and 0, we add A is 0, if we add 0 for A plus 0, the result is going to be 0. So we can think of the last 2 columns here as being a single binary number, a 2-digit binary number. Okay. So 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 2, and this column, this row here, shows us the binary representation for the number 2. So I hope you can see that what we have here is a simple circuit that will do some addition. We've got this carry output from this operation though, so we can imagine if we're trying to build a circuit that's going to add lots of bits together, as well as dealing with the inputs from A and B, the 2 numbers that are being added, we have to be able to deal with this carry out from the previous column. So sometimes we'll have a value to carry over to the next column. We'll need to include that in our operations, and that's where the full adder comes in. The full adder has 3 inputs. It has A and B, which are bits from the 2 numbers that are being added, and it has carry in, which is the bit from the previous column, the carryover from the previous column of addition. Circuit's a little bit more complicated, and there are 2 outputs, a sum output and a carry output. So let's first of all look at our different truth tables here. I've split this up to make it a little easier to see. So we have the different possible inputs for A and B. For the range of inputs of A and B, if there is no carry-in value, so there's no value being carried in, A plus 0 plus 0 plus 0, there's no carry-in, the result is a sum of 0 and a carry of 0. 0 plus 1 plus 0 is equal to 1. 1 plus 0 plus 0 is equal to 1. 1 plus 1 plus 0 is equal to 2. And again, we have the binary representation of 2 here. Now, for the final part of the table, I'm going to add a value from A and B and add my carry in here. So for all of these ones, there is a 1 value being added from the previous column. For an input of 0 plus 0 plus 1, we have a result of 0 carry and 1. 0 plus 1 plus 1, the result is 2, and here again we have the binary value 2, 1 carry out and a 0 sum. 1 plus 0 plus 1, same again. 1 plus 1 plus 1 results in a sum of 1 and a carry of 1, and now we can see here the result here is actually the binary number 3. So we have 3 inputs. In this case, the 3 inputs are all 1, so it's 1 plus 1 plus 1, and the result is the binary number 3. And that's a full adder circuit. Now that full adder circuit adds a single bit. To do some useful addition, you actually want to combine lots of different full adders together to be able to add bigger numbers. And this is essentially how it works. For each adder, there are 2 inputs, A and B, and a sum output. There's a carry in value to each adder, and from each adder there is a carry out that goes into the adder in the next column. So we have our least significant bits. So this is, for example, our units column. We may or may not be able to have a carry in here if there's for example, a value to be added from another number, previous calculation that needs to be added in. But this is our units, our 2s, our 4s, or our 8s. So with a 4-bit adder we can add values up to 15. And we can see that by chaining these together we can carry over the extra bits to try and perform a calculation. Now in the labs we were trying to build these with the LogicGates simulator program, and I should be able to show you this just now. Now first of all, I've got a demonstration of an AND gate, and as we can see here we can verify it works as promised. When both inputs are switched on, and they're red when they're switched on, when both inputs are on, the output is on. Any other case, the output is off. So let's look to our 4-bit adder. Now, I know a few people didn't quite finish this, so I thought I would leave it a little unfinished so we can see how we can wire this up. And again, what you were supposed to do in the lab was sort of build this circuit for a full adder first, and then use the Create IC button to allow you to create from a full adder circuit, create a single integrated circuit that represents it. Having built your IC, if I can get this to add, you can then place them and use them as components, and remember, if you right click you can rotate components round. And I've rotated my full adders just so that the circuitry looks a bit clearer to see what's going on. I've got most of my wiring still to do, but what I have done is I've wired up the carry out from each full adder into the input of the next one. And so we've got a few connections. We've got carry out going to the carry out to carry in, and so on. Let's do the rest of the wiring. Well, for my first full adder, I'm not actually going to have a carry in value, but for each adder I take 1 bit from the first number that's going to be added, and 1 bit for the next number that's going to be added. And I'm going to repeat this as I work along. So I've got 2 4-bit numbers, and the 4-bit numbers are each having 1 bit wired up to a different adder. From our adders, I've already got the carry outs wired up, So let's wire up the sum outputs. And hopefully I've wired this up correctly. And I'm also going to wire up this extra carry out. So I've got two 4-bit values, so I can represent numbers between 0 and 15, and my output is also a 4-bit value. So let me see. Now, you'll note I've changed this to decimal representation, so this just makes it easy for me to put in numbers. So 3, for example, is 0011, 0011, but I can also view this in hex or decimal 2's complement, which is not very useful in this case, binary coded decimal or binary. So we can view this in binary or decimal. I'm viewing these results in decimal simply because it's easier to see what's going on. So I can add 3, and I might want to add 3 and 8. And we can see the result of adding 3 and 8 is 11. Or I might want to add 3 and 9, and the result is 12. We can see from the red wires here what is going on in terms of the inputs to each full adder and the outputs from each full adder. So we can see that here the output is actually a carry output but no sum output. So we're actually feeding a value into the next adder, and again a value gets fed into the next adder. And so we can see a numerical addition circuit being built up out of basic logic gates. So we can start to do really useful things using circuits built up of very, very basic logic gates that do very little individually. It gets interesting when we have a result that's bigger than 15. Well, if we add 6 and 9, our result is 15 exactly. You may sometimes see a little flash just as the results propagate through the different gates. If I add 7 and 15, and the result is 16, and so we can almost imagine that this is an extra binary bit, because this would be the 16s column, or would feed into the 16s column. So the result here would be 16 and 0. I can obviously add larger numbers, and the result again would be 16 plus 2 would be 18. So you can see how this is building up out of the more basic and simple components. We can also double click on a single integrated circuit to see what's going on inside it. And so here's the view of what's going inside that particular full adder. We can see the inputs and the outputs from that one full adder. So if you didn't manage to build the 8-bit full adder, hopefully you can review this and go back and complete that exercise now if you had any problems doing that before. And image credits for this recording are the transistor inverter circuit and title image created by myself, LogicGates, half adder, full adder circuits, public domain images from Wikipedia and Wikimedia Commons, and the 4-bit adder by C. Burnett on Wikipedia.